Hi guys, welcome to Gatematic. In the previous lecture, we have covered single phase half bridge inverter containing RL load. Now in this lecture, we will start single phase half bridge inverter containing RLC type of load, and this is the last lecture of half bridge inverter. So before starting this RLC load, let us do the homework that I have given you in the previous lectures. So I'm not going to discuss this point number 1, point number 2, point number 3 and point number 4. These all are the formula based. How you can find, see, conduction time of each diode is asked in one cycle. It is RL type of load and this is single phase half bridge inverter. So we already draw the waveform of load current. The waveform of load current will look like something like this, and this is my conduction time of diode, conduction angle of diode denoted as phi. Okay, so phi is the conduction angle, but here it is asked the conduction time. So I can easily find the conduction time. See, the time period of this is somehow here. Okay, this is my time period, and time period I can easily find the by taking f naught, that is equal to 1 upon 50 will give me time period that is equal to 20 millisecond. So I can write 20 millisecond will give me the angle that is equal to 360 degree, right? Or you can say 360 degree correspond to 20 millisecond. So 5 degree correspond to 20 by 360 into 5. This will give me the conduction time of each diode in one cycle. Now how to find phi? I already explained you. Phi is the fundamental component of this output power factor angle. So it is equal to tan inverse omega L upon R, and here omega naught I can take. So from here you will get phi is equal to I think 1.799, and based on that, if you will find the conduction time of each diode, it will be 0.09 millisecond. Okay, so point number second is also the formula based, like conduction angle of each thyristor. So conduction angle of each thyristor I already found in the previous lecture, that is equal to pi minus phi. So you can find this. Similarly, RMS value of fundamental thyristor current I can find by integrating, that is equal to 1 upon 2 pi, and from where to where I will get the thyristor current from phi to pi I01 max omega naught t minus phi 1 chi square into d omega t. Phi 1 I can easily find by using this, that is the first point, and I01 max I already explained you how to find, that is equal to 2 VDC upon pi into Z1, and Z1 will be equal to under root of R square plus omega naught square L square. So based on this formula, if you will integrate this, you will get the thyristor fundamental thyristor current and RMS value of fundamental diode current. So these two are very easy. Only you need to do the mathematics part. Now see the fifth and sixth point that I haven't explained you in the lecture, and I told you that give me the answer in YouTube comments. So most of the students have given me the answer of this question. See, it is saying for how many duration in millisecond load is delivering power to source. See, if you will draw the output voltage, then output voltage will look like this. From 0 to t by 2, it will be VDC by 2, and from t by 2 to t, it will be minus VDC by 2. Now if you will draw the instantaneous value of load current, then it will be exponential but shifted by some angle phi that we have discussed in the previous lecture, like this. Okay, and this is my time period t, this is my angle phi. Now see, from 0 to phi, output voltage is positive and output current is negative. So I can say P naught in between 0 to phi will be negative. I can say that. That means from 0 to phi, load is delivering power to the source. Are you getting this? In the same way, you can see this is my, this will be somehow here. In the same way, you will see that from t by 2, this is my t by 2, or you can say pi, from pi to, this is pi plus phi. You can see the V naught is negative and I naught is positive. So in this time also the output power will be negative in between from pi to pi plus phi. Is it fine? So I am getting negative power from 0 to phi and from pi to pi plus phi. That means in one cycle I am getting the negative power for 2 phi, and it is asking that for how many duration load is delivering power. This is my degree. Okay, so if the question will be something like this, for how many degree load is delivering power to source, or for how many angle load is delivering power to the source, then the answer will be 2 phi. Now I need to find the time in millisecond. So what I will do, I will just write 360 degree correspond to 20 millisecond. Okay, so 1 degree correspond to 20 by 360 millisecond. So 2 phi correspond to 20 by 360 into 2 phi millisecond. And how to get phi? I already told you that is equal to tan inverse omega L upon R. This is omega is the fundamental frequency. Is it fine? In this way we can calculate. Similarly, see the sixth part. For what angle source is delivering power to the load? Source will be delivering power to the load when P naught will be greater than 0. So see from which duration to which duration P naught is positive. From phi to pi P naught is positive, and from pi plus phi to 2 pi, this is my 2 pi, P naught is positive. So overall I can say for 2 into pi minus phi, P naught is positive in one cycle. I can say that. Okay, so answer of this will be 2 into pi minus phi. Got it? In this way we can solve the question number 5th and 6th. Now let's proceed to single phase half bridge inverter containing RLC type of load. So same procedure you have to apply in RLC type of load, only the waveform of I naught will change. See, the waveform of output voltage will remain same. Why? Because this is the voltage source inverter, and in voltage source inverter, the load voltage is independent of the load current. So see here, in all type of load, whether it is R load, RL load, RLC type of load, the output voltage will remain as it is, and the peak value will be VDC by 2 and the minus VDC by 2. And if I will have to draw the fundamental output voltage, then it will look like this. Okay, this is my fundamental output voltage, that is equal to V01 of t. Now I need to find the value of I naught of t. See, from 0 to take any time, if you will see this switch S1 is on, then in that case this plus VDC by 2 is directly connected with the load, and load is having RLC type of load. So DC excitation, this is VDC by 2 for some particular value of time is connected with RLC type of load. So how the transient current I naught of t I will get? The I naught of t will be sinusoidal because of the second order circuit. Because of the presence of L and C in the circuit, the current you will get, that will be sinusoidal in nature. So overall the current, load current you will get, that will be sinusoidal. Now based upon the value of XL and XC, we can determine whether it is lagging or leading load. Okay, so if I am considering the lagging load, then the output current will lag behind by voltage by angle phi. Okay, so it will be something like this. See here, output current is lagging by angle phi. This is if I will consider XL greater than XC, means when lagging load is taken, or you can say in over damped case. Now if XC will be greater than XL, means if capacitive reactance will be greater than inductive reactance, then in that case the current will lead the voltage by some angle phi. So in that case the waveform of output current I will get something like this. Means the output current will be leading in nature, means when value of XC will be greater than XL, and this usually occurs in underdamped case. In control system, you will study in detail what is underdamped and overdamped. In underdamped system, the value of zeta will lie in between 0 to 1, but in overdamped system, the value of zeta will be greater than 1, and you can easily find by taking the value of L and C, the value of zeta. Okay, so if you will see the value of XL is greater than XC, then normally it is considered to be overdamped system, and if the value of XC is greater than XL, then in that case the system is considered to be underdamped system. You can find by finding the value of zeta also, no issue. So finally I can say for leading load, the waveform of current will be leading by voltage by some angle phi. See here, it is leading by angle phi. This is my angle phi. Similarly for lagging load, when XL will be greater than XC, then it will be considered as a lagging load. Then in that case the waveform of current will lag behind voltage by angle phi. Now see the conduction angle of each element. From 0 to 5, if I will take the lagging load, okay, first I will analyze the lagging load. From 0 to 5, you can see the I naught is less than 0 and V naught is greater than 0. I naught is less than 0 and V naught is greater than 0, means in that case D1 will conduct. So from 0 to 5, D1 will conduct. Similarly, from 5 to, let us say this is pi, and this will be my 2 pi. Overall time period will be this will be my 2 pi. So from 5 to pi, V naught is greater than 0, I naught is greater than 0, means switch S1 will conduct. Similarly, from pi to pi plus 5, see, V naught is less than 0, I naught is greater than 0, means in that case D2 will conduct. So this will be my conduction angle of D2. Same as the previous case, only the waveform I will get here, that is sinusoidal. In case of RL load, the waveform is exponential. Only the waveform will change, but the conduction angle you will get same as the previous one. Similarly, from pi plus 5 to 2 pi, V naught is less than 0, I naught is less than 0, that is switch S2 will conduct. So this is my conduction angle of S2. So I can say conduction angle of each diode is equal to phi, and conduction angle of each thyristor will be equal to pi minus phi, same as the previous case. In the same way, I can find for leading load also. Okay, this will be my pi minus phi. So from 0 to pi minus phi, you can see V naught is greater than 0, I naught is greater than 0. In that case, S1 will conduct. From pi minus phi to pi, I naught is less than 0, V naught is greater than 0. In that case, D1 will conduct. So this is my conduction angle of D1. Similarly, from pi to, this will be my 2 pi minus phi. V naught is less than 0, I naught is less than 0. So V naught is less than 0, I naught is less than 0, means switch S2 will conduct. This is my conduction angle of S2. And from 2 pi minus phi to 2 pi, V naught is less than 0 and I naught is greater than 0, means switch D2 will conduct. This will be my conduction angle of D2. So here D2 is conducting. Okay, so I found the conduction angle of each diode and conduction angle of each thyristor. Whether it is leading load or lagging load, the conduction angle will remain same. This is my leading load case and this is my lagging load case. Now see, in which case force commutation is required and in which case self commutation is required. Let us understand this. This is really important. So see, if I will take the lagging load first, then see, D1 is conducting from 0 to 5. D1 is here. Okay. After D1, switch S1 is conducting, okay, and D1 will off. Then when S1 will get off, then D2 will conduct. When S1 will be off, then D2 will conduct. Fine. And when D2 will be off, then S2 will conduct. So in this case, we need forced commutation, okay, because we cannot disconnect the, or we cannot close the switch by self. Okay, we need some external circuit to turn off the switch. Now see the leading load case. From 0 to pi minus phi, S1 is conducting in leading load. So let us say this is S1 is conducting. After pi minus phi, D1 will start conduct. See here, after pi minus phi, D1 will start conduct. So the moment when D1 will start conduct, then the voltage drop across this D1 will be forward voltage drop, and this is approximately 1 volt in power electronics. So because of this forward voltage drop across this D1, this switch S1 will go into the reverse bias. Let us consider this switch S1 is thyristor. Okay. So initially S1 was conducting from 0 to pi minus phi. Okay. Now after pi minus phi, when D1 will start conduct, then the voltage drop across this D1 will be equal to 1 volt, and this 1 volt is applied across the thyristor S1. Okay. And this thyristor S1 is getting negative 1 volt. So because of conduction of this D1 will make this switch S1 go into the reverse bias. So in leading load, I can say self commutation is possible. However, this is not the case possible in lagging load. Why? See here, in lagging load I already explained you that let us take this D2 or let us take this S1. Okay. So when this S1 is conducting, let us say this is thyristor and this is conducting. Okay. And after S1 means after pi, D2 will start conduct, and this is my D2. So this D2 is not responsible for reverse biasing this S1. Okay, if D1 will conduct, then definitely the 1 volt potential will drop across this S1 and this S1 will be turned off. Okay, but in this case, in lagging type of load, after S1 D2 is conducting, so this D2 is not responsible for self commutating this S1. So in lagging type of load self commutation is not possible, and in leading type of load self commutation is possible. Now under self commutation means under leading load, the question they will ask you about the circuit turn of time. So we know the circuit turn of time is defined as the time for which thyristor is reverse bias, and this is my thyristor. Okay, so this thyristor will reverse bias till this D1 will conduct. Okay, so when the D1 will conduct, then the voltage drop across this will be 1 volt, and this negative 1 volt is applied across this thyristor. So this thyristor will be reverse bias till this D1 will conduct. So see that conduction angle of this diode D1, conduction angle of this diode D1 is phi. So I can say this thyristor S1 will face reverse bias till this diode D1 will conduct. Okay, so this diode D1 is conducting for phi duration in one cycle. So I can say omega Tc will be equal to phi. So Tc will come out to be phi upon omega. This is really important. Generally in case of leading load, the circuit turn of time they will ask you, so you need to find the circuit turn of time like this. Tc will be equal to phi upon omega, where phi will be equal to tan inverse xc minus xl upon r. You can take mode also, no problem. Okay, so in this way you can find the circuit turn of time. Now let us derive each and every parameter related to single phase half bridge inverter containing RLC load. See the first point, conduction angle of each diode I already got, that is phi. Conduction angle of each thyristor that I already got, that is pi minus phi. These all things I have explained you. Third point is really important for RLC type of load, that is self commutation is possible only in leading power factor. The detailed explanation I have already explained you. Also in leading type of power factor type of load, if self commutation is possible, then I need to find the circuit turn of time Tc, that is equal to phi upon omega, where omega is the fundamental frequency. Fourth point is same for all kind of load in single phase half bridge inverter, that is Fourier series expression of V naught of t, that is equal to summation of n is equal to 135 to infinite to VDC upon n pi sin n omega naught t. This is same for all kind of load. Now if I will talk about the I naught of t, I already know I naught of t is equal to V naught of t upon Zn. So V naught of t divided by Zn, it is shifted by some angle phi n obviously, but this plus or minus will depend upon whether it is leading type of load or lagging type of load. Okay, if the value of phi n you will get in negative, then it will be in minus, that means it is lagging in nature. If the value of phi n will be positive, then it will be leading in nature. Okay, so I am taking plus by default. You will get the answer in negative or positive by finding the value of phi n by using this formula. Similarly, I can find the value of z, and these all concept I already explained you, as we know that mode of z is equal to under root of r square plus xl minus xc ka whole square. Now this xl is depending upon the frequency, so it will be n omega naught l minus 1 upon n omega naught c ka whole square. That is what I did while finding the value of Zn. Okay, now see the fundamental displacement factor, that is the fifth point. Fundamental displacement factor is the cosine of angle between fundamental component of current and voltage. So angle between fundamental component of current and voltage is shifted by some angle phi 1, so I can say cos phi 1. Okay, sixth point is really important, that is the diode and switch current waveform. I am talking about the fundamental only, because here fundamental I am getting sinusoidal in nature in case of RLC type of load. So I already got, that is the wave, each diode, this diode D1 will conduct if I will take the lagging load. Whether it will be lagging or leading, it is only shifted by some angle. Okay, so RMS value or average value will not change. So I am considering by taking example of lagging load. So this will be my phi, and this is thyristor current or switch current is conducting from phi to pi. Now once I got the waveform, then I can easily find whatever the question is asking. Like if I will have to find the average fundamental value of average diode current, then I can easily find 1 upon 2 pi 0 to phi I01 max sin omega naught t minus phi 1, and I am taking this minus phi 1 considering lagging load. If leading load you will take, then it will be plus phi 1. Overall the average value will not change. Okay, now how to find the I01 max? I01 max I can easily find by using this Fourier series. So I01 max is nothing but it is equal to V01 max upon Z1. So it will be equal to 2 VDC upon pi into Z1, and Z1 I can find by putting the value of n is equal to 1 by using this equation. Okay. Similarly, RMS value of diode current I can find. Once I got the waveform, then I can easily find the diode average diode current, RMS diode current. Similarly, for average switch current, or you can say thyristor current, and RMS thyristor current. Okay, each thyristor is conducting for pi minus phi duration, so I can integrate from phi to pi, and I can get whatever the question is asking. So this much amount of concept you need to understand if RLC load is taken. And in RLC type of load, only this point number 3 is really important, that is self commutation is possible only in leading power factor type of load. So based on today's lecture, let us solve one homework. A single phase half bridge inverter, R is equal to 3 ohm, X is equal to 10 ohm, and XL is equal to 6 ohm. This is the RLC type of load is taken, and VDC by 2 is 100 volt, and fundamental frequency F0 is given, that is equal to 50 Hz. Now you need to find the circuit turn of time of switch. Okay, so find the circuit turn of time of switch and write down your answer in YouTube comment. I will explain you correct answer in the next lecture. For doubt solving, you can join our Facebook group.